If you look at the picture, yes, you go to the museum, yes, you feel that this painting is beautiful, yes, and this problem is beautiful, so there is such a notion as beauty most probably in mathematics, which is an important part of mathematics. I have this strong belief that in this so-called high-level mathematics, they have all the language, they develop theory, but many times actually they hide. Then at the heart of the proof actually there is a not combinatorics but combinatorial idea. Now the combinatorics is a little bit considered a more serious subject. Now even the mathematicians who are working on some other much better established area start to understand that at some point even there a very huge part of the result contains combinatorial like ideas.
Already in the fourth-term arithmetic progression, you reduce the problem to basically a problem about graphs, and at least for the general solution, you need to use what is everybody calls the celebrated Semerad irregularity lemma. Can you explain the lemma?
The regularity lemma states that you can break the graph into pieces, not too many pieces, so that the resulting bipartite graphs have all the nice properties. The whole graph is a chaos because you just don't know what are the edges, but then you can break it down so with big pieces so that there is a almost total order.
I mainly want to talk about problems. I think combinatorics is a very different problem, a different area in mathematics than most other areas, at least the way they are viewed. So to begin with, what was your first result?
My first result was, if I remember correctly, not in combinatorics but in number theory. At the very beginning I started to work with András Sárközi, who is about of my age, and Paul Erdős, and we worked on actually, this is not analytic number theory, it's combinatorial number theory, so it's part combinatorics, part number theory.
Can you explain the problem? Is it simple enough?
The problem is something like that, maybe one typical one, there was a sequence of integers, and then what density will be enough so that there is an infinite subsequence, so then each divides the next one. So what is the condition? We got a sharp result on this, and then the variation of that kind of problems.
How old were you?
I was 24 or 25.
So this was a part of the PhD?
No, not really. It was just that I studied as mathematics physics teacher for 2 years, and then you had the possibility to switch and to be a mathematician. And it was in the third year. And then I met Paul Erdős and András Sárközi, and when I was in the 4th grade, then we started to work together. So it was not toward the PhD. It was well before the PhD.
Many of your colleagues in Hungary, they started working on mathematics very early as teenagers, and in fact they met, I think some of them met Erdős and Turan and these people much earlier. So how come you started so?
Well, I was lucky enough not to start that early. I worked in mathematics even in the elementary school, in the sense that I solved exercises for somebody, mostly for the stronger ones, just to get a defense if a stronger student attacked me, then the even stronger one protected
Stronger
me because
this way.
stronger physically.
Yeah, I did the same.
That's a good thing. So mathematics is good for something. Obviously, I already realized it at a very early age. But that was it, just exercises, the usual exercises in the elementary school. And in the high school, I haven't studied mathematics, just like the ones with the material, strictly the high school material, because my father one's dream was that I would become a physician. And so I had to study biology. And at that time, the entry exam was very, very difficult. It was in the 50s, more exactly 58, and then that profession was highly regarded. So it was a big competition, just like now in mathematics. So in the high school, I didn't do anything more than the usual things. But you are right that in Hungary and most probably in US and I am sure in Israel too, there are very special schools when they actually produce this genius. Like in Hungary, the Fazekas, when they are 15 or even 14, they already get a very serious education. Fazekas is very mathematically oriented high school, and there are many others, 3 or 4 others. So in every year, they produce at least 20, and this is just my estimation. I don't really know the exact numbers, who by the time they get to the university, they already know a lot. Well, you know some of them, like, of course, maybe the most famous is Lovász, but Lackovics, Porsche, Pelikan, and others. Many became famous mathematicians. I didn't follow this path for different reasons. I went to the medical school, and after half year I realized, actually a little bit earlier, that it is not for me, because you had to work very hard, and also being a physician is a really very stressful profession, and you have to be somebody who really from the morning to the night cares and then about the patients, and I was scared, to tell you the truth, and that is why I stopped, I dropped out. And it had some consequences that when my father asked me then what are the news at the university, I told him that, well, ask my friends. I cannot give you an updated information, and then we had some difficult time after that for years.
For him to accept the fact.
Yeah, for him to accept the fact that yes, I am not there anymore.
You think that parents should plan a path for their children in life?
Yes, that is my belief. Then they should plan a path for them, but also they should be aware that it will not work out. So you can plan anything, and then most probably, well, in some cases it helps, but definitely not in that regard profession. But for instance, if you plan the marriage of them, like in India, then it I know I had many Indian students. It helps actually. Their marriage most of the time works out fine, but most probably in profession it doesn't work. And anyway, I had the plan, but nobody listened to me in the family. I have a very charismatic wife, you know, Anna, so I have no chance to be heard. So whatever she wants.
No, but she's a parent.
But then she is so mild, and she agrees whatever they want, and some of them went to the universities which I actually disprove. And people believe that I was the one who advised them to go there. No, I was not the one. So I am still have to explain to everybody why I sent them there. First of all, they didn't listen to me, and I didn't send them there. I would have sent them somewhere else, because they are very much in humanities. Mm-hmm. And then now they studied economics, and they never studied mathematics, and study economics without knowing practically anything about mathematics is an extremely difficult. So they had a very hard time, and so we have 5 children. The other ones had a little bit easier path because they choose what they really are good at.
There's a famous Hungarian story with the Polgar sisters, where it seems that the parents, the father, more or less decided in advance that these girls will be chess champions, and that's all. So, what do you think? It is extreme, or?
Well, that is a very controversial issue in Hungary because the Polgar, the father of the Polgar sisters, there are 3 of them. Yeah. And one of them, not even the best one, was the world champion among the women, but then he didn't let the best one, namely Judith Polgar, yeah, who just took part in a competition with the men. She wanted to be a world champion among the men, and Kasparov, we all know Kasparov, he is not a very shy person. So, and he told, of course, not in US because he is cleverer than that. He told it in Russia, that the woman can never beat the man, can never be a world champion, and so far he's right. Most probably, if they let Judith Polgar to play among the girls when she was 13, and she would have become a world champion like 14, and then just switch it and then have her play only with the men, then maybe then she could have been a little bit better. I don't know. But this Polgar he has a real unbelievable ego.
Oh, you know him?
I talked to him, but I wouldn't say that I know him. I just ran into him. In the family there is a famous person who is a television producer, and then he made I don't know, a movie, but something with the Polgar family. Actually, he wrote a book about Judith Polgar. So I just by chance I met Polgar at his house, but I didn't really talk too much about him. But he claims that regardless, choose randomly 3 children, he will make them world champions, but not only in chess, choose like mathematics. And then all of them, all 3 will be world-class mathematicians. So I told him, look, choose me and 2 others, and let's see the result.
What do you think makes mathematics so much harder to train somebody to be a top mathematician than to be a top chess player?
I believe then Polgar just got lucky because in the earth there are 7 billion people, and he was the one who had 3 gifted, it just happened to be the case. Then he was the one who had 3 brilliant gifted daughters. Actually the third one gave up chess very early, so she became a very good one, I guess a grandmaster among the women, but that was. But then she decided that she will quit because it is not her life. So, well, of course, it is very spectacular having 3 daughters and all of that. But look, most probably one can choose in some other subject or even in sport, such a thing that the father even the father is good, and the children are excellent among tennis players, definitely, or soccer players.
But you don't think that mathematics is different than this, that doing mathematics well as research?
It requires different skills and abilities. But it could be then you have 3 children who are born to be genius mathematicians, and then you start to, just like in Fazekas. It's just like in Fazekas there are 10 genius, like in the last 5 years, and let's assume that it could have been then 3 of them were identical twins, for instance.
most of the people who worked with Erdős when you worked with him were younger. I don't know, how many people did he work with when he was visiting Hungary?
It is hard to judge, but a positive percentage of the students, of course, this could be then one, right? But at least 10, I would say that at least 10 students or young researchers who just finished the university was around Paul Erdős, and then they worked together. And definitely, if they didn't work together, they worked on Paul Erdős's problem. So he was the most influential mathematician at that time. In the early 60s in Hungary, combinatorics was one of the main area, which was not good, in some sense bad, because it was a little bit one side. Of course, we had algebra, geometry, and some other things, but for instance, we haven't had a school on algebraic geometry, differential geometry, really good school, or low-dimensional topology, and so on. I only name this one because I know the name of these subjects, not that I really know these things, but that I at least could see that it was one-sided. And the reason is twofold. One is that Erdős was extremely influential, and also his problems are such that you could start to work on it without studying too much. Of course, some of the problems were very difficult and then you failed. But at least on the surface, it seems to be that you can attack, as opposed to, let's say, a problem in algebra, geometry. You really have to study before that 2-3 years before you really have a reasonable chance to start to work on it.
Just understanding the definition.
Yeah, exactly, learning the definitions or learning the basic techniques.
What was the interaction like between Paul Erdős and the people he worked with? How did it function?
He usually sit in the main office of the institute, which is now called the Alfred Rényi Institute for Mathematics. At that time it was Institute for Applied Mathematics, if I remember correctly. Maybe the applied was not added, but it definitely started in 1953 as an Institute for Applied Mathematics, and Rényi was forever, until his death, was the director of the institution, but he let Erdős to sit in his room, which was the room of the director. It was beautiful, old, like 150 years old. The whole building, it's a very nice building. So and then people, he invited 2 or 3 people or students at the same time. I have almost never seen him talking on one-to-one basis. At least 2 or 3 were around him most of the times. And then he invited students for a lunch. At that time it was a big deal. Astoria was a more or less famous hotel, and he invited some of the students, including me. So he worked like this, and then he asked questions, and then the students could sit in the room. It was very comfortable. Everybody was very happy when he could talk to Erdős, and then there's a lot of very important problems. So he had some gift which most probably nobody at that time had. Then he asked a lot of questions, and somehow magically it turned out to be the case. Then most of his problems were basic problems, even the ones which didn't require a difficult solution. Some of them, of course, were the ones which we already forgot, but most of them was really important questions.
Do you think now, with all the experience of so many years, you can... in combinatorics, it's very easy to make up problems, and other people make up problems, and we can make up as many as we want. That would make sense, at least as mathematical problems, and probably many of them will be just boring. So do you understand this gift that Erdős had?
It's a God-given gift. I don't know how he in almost every day he came up with some important question. Well, he asked something, maybe it was not so interesting, but next day he realized that he could modify it, and then the problem became really interesting. It's many times it happened. So he was just so much in mathematics, and especially in combinatorics. And he was there are different type of mathematicians. He was the one who was of course asking questions after questions, and then many of them, then he for the solution he worked with others, or he solved it sometimes, but mostly I guess he almost never had a paper alone. He always had a co-author. But that is a very special gift, and there are other mathematicians who build theory, but Erdős never, I am sure, never was interested in building theory. He was always interested in solving actual problems, posing them and solving it. As you know, then he offered money for the solutions. He had to know very well that the Hungarian salaries were very low, because he offered such amounts, and even if when you solved it, then you got so much money, which was actually much less than the minimum wage.
So he could evaluate the difficulty of the problems he asked well.
I don't know. There were $10 problem was which still open, and it's getting more and more interesting. And there was $100 problem which has been solved soon at that time. So I don't know, but mainly he had the right hierarchy, meaning that he offered more money for the more interesting problem. So he almost never made big mistakes. I mean, by offering, and of course, money was just a symbolic thing. He sometimes paid with check, though at that time you couldn't cash it in Hungary, but then people kept it as a souvenir.
What is the thing that makes it basic or important? Because again, we agree that there are numerous questions you can ask. Is it the fact that you need a new method to solve it, or you discover it's only with hindsight, only after it's solved you know that it was a good question, or you can tell in advance?
There are some questions like the sunflower. It is absolutely interesting on its own, right?
Can you explain it?
Yes, somewhat, yes. So we have n-element sets, and then what we are interested, then how big how many sets we have to have, so that there we always will find 3 of them, so that their pairwise intersection is the same. So it looks like a sunflower. That is why it is called the sunflower problem.
So
that the intersection is the middle of the sunflower, and then these 3 ear patterns are disjoint.
I completely agree. It's a very interesting problem. I tried it myself, but probably not close to the amount you put into it.
That was the first problem really what I wanted to solve when I was university student. I heard it from Paul before we started to work on these elementary number theory problems, and this was my favorite problem. Yes, I put at that time a lot of time, and I am planning to put even more time in it, although I am well aware then the probability that I can solve it is very little, and even to make a significant progress, because most probably it is just not something that you just can attack with brute force and then this or that simple idea. It should be deep. Most of the combinatorists worked on it at some period of their mathematical career.
So it's a really interesting test case, I think, for me to probe what makes a problem interesting. Of course, you could state it in one sentence, We know that the size of such a family has to be at least, if these are n-element sets, and it has to be at least something like 2 to the n. We know that if we have n to the n, then it's enough. And these are all simple arguments. And so the question is, what is the truth in the middle? It doesn't look like such a big gap. But, you know, for a bystander, I mean, a bystander mathematician, would wonder why should you or any other combinatorialist invest years in trying to figure out this particular one as opposed to, you know.
Well, you don't give an answer to the bystander. Yes, that is the right solution. It's just clear. Really, nothing more can be said because we don't know whether the solution will. It's a beautiful problem. I mean, if you look at the picture, yes, you go to the museum, yes, you feel that this painting is beautiful, yes, and this problem is beautiful. So there is such a notion as beauty most probably in mathematics, which is an important part of mathematics. Without it, mathematics would be, at least by my opinion, is much, much poorer. So definitely for me, this is a beautiful problem. And most probably, but that we of course cannot say with certainty, will require methods which will move combinatorics and some part of combinatorics and will be applied in many other areas. I just cannot imagine that without methods you can attack this problem. So maybe actually this will not be a problem in discrete mathematics, but maybe we need, yes, continuous mathematics and different branch of mathematics. At least we have to adapt either the technique or the results. I don't know, I am just guessing. I have a plan to work on it again. Look, that is one advantage, not too many advantages are to be old, but that is one then without any risks you can not produce anything. Especially in US, they don't fire you, yes, they just cannot fire you if you are over 70. So
this problem, I mean, of course, this feeling that it's beautiful and basic was vindicated long ago because it, even the weak bounds we know were used in lots of areas. In fact, just a number of computer science papers in which it is used to a really important effect. Mainly the upper bound is numerous, and it comes in matrix multiplication. It comes in pseudo-random generators. Some problems which are stated just in the same ease, very elementary about a set of family of subsets, resist solutions which are combinatorial themselves and often, let's say, even without using any heavy mathematics, require just the use of linear algebra, but require in the sense that we don't seem to have other methods to solve them. To what extent do you believe that using combinatorial methods or elementary methods for elementary problems in general is sufficient?
no, it's not sufficient. You just mentioned some in computer science when it's the problem itself really of a combinatorial nature, but the solution requires at least linear algebra, and this is beautiful. It works like magic, and without it they cannot solve. And then in number theory there are many problems where actually in arithmetic combinatorics, which are combinatorial nature, but we know then the solution requires either higher order Fourier analysis or ergodic theory, and then they get stronger and stronger results. So I am a strong believer, though it works against me, that yes, for solving combinatorial problems you will need more and more to borrow tools and even ideas from different branch of mathematics, but that actually makes the combinatorial problem more interesting and say even deeper, yes, and then the solution requires interplay between different branch of mathematics. That is what really is the thing which makes the problem and the solution very interesting. And then usually what happens, and once you do it for one thing, then most probably then you can apply the same ideas, not exactly but similar, to solve some other problems, actually problems which are seemingly far from your original combinatorial problems. So you are theoretical computer scientist, so you know this phenomenon very well, that this happens more often than not. And I am very happy for that. Unfortunately, unhappy that I don't know these tools, but actually I decided to study mathematics now. I am not joking, it's a very serious thing that my original plan was to go back and what I missed at that time, because I didn't start as a mathematician, and even the first 2 years was for physics and mathematics. And for some strange reason, even after that, the professors were not at home at that time. Rényi, Turan, some were abroad, so we didn't get a real good education. And once you are 25, you don't get good education. You have to be or very, very devoted to mathematics and hardworking, or you just give it up and then work on a problem. So I am unfortunately belong to the second group, but I always felt the need. But to feel a need to study and actually study is unfortunately two different things. But now I really started to study things which I wanted 50 years ago. Well, it's a very slow process. I feel that I have been slowing down considerably, though my interest is more intense than it was 50 years ago. That is a strange contradiction. But you need for combinatorics, even if I want to solve a problem in combinatorics, and I would like.
But you know which tools you think you will need in order to solve them?
Well, I guess, yes, I guess. So now I am studying harmonic analysis, but on the elementary level, I really, if somebody told me then in Budapest, I spend most of the time in Budapest now, that there is a class on this subject that then I would sit in. Though most probably my color of my hair would make it a little bit strange sitting here. And then of course to color it's just too much price for the knowledge.
It's hard to know what to use, even if you are, even if it's definitely within your range of tools. I had another example of a problem that I believe you think is basic and you worked on. So this is a Heilbronn problem. So maybe you can describe it also.
It's a beautiful problem, and Rod, one of the Fields medalists and one of the greatest mathematicians of the last century, worked a lot on it. So the problem I just will formulate first for triangle, and then later a little bit more general, because in the general case nothing practically is known. For the triangle something is known. So the problem is the following, that you have a unit square and the devil puts down and points so that you consider all of the triangles.
So all the triangles at this endpoint.
Endpoints, which is, we call it then the number of triangles n choose 2, which is approximately, let's say, n to the 3.
N choose 3, yeah.
N cube. And then you actually choose the triangle which has a smallest area. And then Heilbronn conjecture was that the devil cannot do a very good job. Maybe the smallest area always will be less than 1 over n square. Regardless how the adversary puts down the endpoints, it will be always a tiny, and tiny in that case means 1 over n square. And that was for the triangle. And then they started to to prove it step by step, improve the bounds, like Ross was the first one who proved that, okay, not 1 over n square, but always there is a triangle of area 1 over n times log n in the denominator. Then Wolfgang Schmidt, again a giant in mathematics. You see the Wolfgang Schmidt work and both Ross on a very important problems. Nevertheless, they consider this one an important one too, though many might disagree. So then, with the beautiful proof what Wolfgang Schmidt gave, stated that there is always a triangle, that the area is at most 1 over n times log n. N times log n is in the denominator. Yeah. And then he took a completely different approach of Ross. According to him, he worked 5 years on it, and then he proved that there is always a triangle of area 1 over n to the 1 plus, let's say, 1 over 100. But still, 1 plus 1 over 100 is far from 2. Yeah. So that is now the art of the state of the art, at least as far as this problem is concerned.
Well, you refuted...
yes, but yes, with Miklós Ajta and János Komlós, we refuted the conjecture which is called Heilbronn conjecture, stated then 1 over n square is the right bound, and then there are random construction and deterministic construction. Actually, the nicest is due to Paul Erdős, where there is the n point, so that the smallest area triangle is of area 1 over n square. But then we use the so-called pseudo-random method, which at that time was not called pseudo-random method, and we disproved. Then we actually semi-randomly, whatever it means, constructed n points where the smallest area triangle had an area log n over n square, but still n square, so nobody knows whether 1 over n to the 2 minus epsilon is true or not. That is a major open problems, because already Ross solution required a lot of mathematics, Fourier analysis, functional analysis, and then that kind of stuff. It was striking how he came to that idea. But now let's see that you are interested in the following thing, that you consider 4 points. So if you consider 4 points, what could it be then? A triangle, 1 point inside, or a foregone? Yeah. Yes? And now the same question. You are looking for the smallest area. It is small, well, of course, it's always smaller than 1 over n. It's easy to prove, right? It's not even at most high school exercise, but actually a very good 8th grade students in elementary school could solve it. But nothing known, then it is just slightly less. Little, meaning that less than 1 over n is not known. That is would be the first step. And in the another direction, which is unbelievably interesting, but it's a great problem, is that there is always a triangle of area 1 over n which contains k points.
This is a result of that?
No, that is, of course, that would be much stronger than the previous one, because, yes, that is a conjecture that even this true. Fix any k, and if n is large, then you always, and then you put down n points, then you always will find a triangle containing k points.
With area 1 over n.
With area, of course, 1 over n. And what would be the expected number of the points? 1. Yes, because you have n points, the area is 1 over n, then you expect in average at least 1 point. Instead of that, you have k points. It's very far from the expectation, but that is true. Almost sure must be true. But the proof would really now require so-called real mathematics. I'm sure then you, within the usual combinatorial arguments, whatever it means exactly, you cannot solve this problem. But there is another problem which is equally interesting. Then regardless how you put down n points, there will be always a triangle of area now k over n, which is empty.
Now you want a lower bound, yeah. You want to say that there is a large, it's an opposite game.
The opposite game, exactly. So the opposite. So there are discrepancies in both ways. Too many points or too big triangle, or just too big empty triangle.
These problems are comparable to the sunflower problem?
Yes, they are. That's comparable. We don't know, yes. And in beauty too. I mean, if you read the Rose solution for that, it's just completely
No,
out of
before you know the solution, whether it's clear that it's so.
Well, this most probably is clear, then it is a very difficult problem.
Why did Heilbronn ask it?
I don't know. There is a story that then he looked out the window and the soldiers were marching, and then I don't know what is the connection between them and that. So it's just.
So that's how basic problems come about.
Right. So if you don't have a army, most probably then some of the basic problems will not be asked.
Steiner triple system. I think he was watching out the window and looking at the schoolgirls that were passing.
Right, yes, it was good then they were girls maybe, yes, and not boys. We don't know, of course.
You seem to have a special love for geometric problems, and in particular incidences of lines and points. Maybe you should tell about the Semeredy-Trotter problem, but where did this problem come about?
You separate the projective plane, which I am not going to explain now, from the Euclidean plane. And in the following way, then the incidence relationship is different in the two planes. It boils down the following thing, that you, for instance, want to prove that if you have n points and lines, so that on every line there is at least k points among these n points, then how many such a line can be? And then we gave an upper bound on it, then at most n square over k to the 3.
Mm-hmm. So this is in the real plane, in the normal plane, the number of incidences is much smaller than in the projective plane.
Right, so that separates the two things. So the problem started, which is somewhat interesting. Yes, we always like separation result. Well, in theoretical computer science, that is the big deal.
Yeah, so this is two models of computation, the hyperbolic plane and the real plane. And this is a problem of Erdős also?
Whether this one was Erdős's problem, I am not sure. Whether it was already in the literature. But it could be that it was Erdős's problem. But definitely when we started to work on it, we didn't know it.
And the methods there are elementary, the proof that of this...
Yes, the method is elementary, and it was very long, complicated, and then a Hungarian mathematician gave a solution 2 pages, so I just wanted to be below the... just shrinking, I just wanted to shrink to a size so that nobody would notice me.
Well, but he's still using your result on the crossing number in the graph.
But I knew the crossing number at that time, yes, so I could have used it. But maybe, yes, it is a false modesty, then you don't use your own result to prove another result. I don't know, but definitely Székely's proof is a pure beauty. It's just like, as you know, Erdős said always, and there is a book, the God has a book, and then in the book always there are the most beautiful solutions are written in the book, and I am sure that this is in the book, this solution. And then they use this result in many different, for many different problems.
The real breakthrough again was to move not to from the real plane to planes over finite fields, where the same question showing that there is still a separation between finite fields and the projective plane had sort of remarkable application.
In computer science, you were one of the leaders of this. Then you really used this. It is important. It's absolutely basic. But I wouldn't say that the authors, yes, who proved it, yes, Terry and then Katz and Burgen, yes. You were inspired by our result. It was most probably they were inspired by you or the theoretical computer scientists.
In this particular case, I know very well. We had a problem about randomness extractors. We had an idea of what we would need to solve it, and it was more or less the sum product theorem, which is sort of equivalent to this point line incidences in finite fields, and we had no idea how to prove it. And then Burgen gave a lecture here, and we went to accidentally to the lecture and understood that this. So they were certainly not motivated by this. I think they were partly motivated by your result. They definitely knew about it, that it will be an analog to your result in the finite field case, and they were motivated by analytic consequences of this theorem, which they went on to produce. Maybe to you it's not surprising at all that these basic problems, like incidences between points and lines, that maybe Euclid could have worked on, find applications in mathematics. So beforehand we talked about the other direction, right? We talked about using tools from mathematics, from algebra, topology, etc., to solve combinatorial problems. So here we see that combinatorial problems, innocent combinatorial problems, can be at the heart of solutions to, once you solve them, it can be heart of solutions to problems in analysis, in algebra, in computer science, and so on. So is this surprising or this is expected?
I always like analytic number theory. And because this is still concrete, so I cannot understand abstract things, but analytic number theory is still something which you can grab. Because it's computation, yes. Once you learn a little bit complex function theory and so on, and then it's computations almost the same way because we work also in probability theory, so sometimes we had to compute things, so that was not so far from my taste, and I always liked it. I am pretty sure I became a mathematician after hearing Turan's lecture, which was on mainly on analytic number theory, and it was given to mathematics physics teachers, which was very remarkable because there were 200 students, so it's you know that it is very hard to speak to a completely diverse audience when some of them, and he managed even the very, it's maybe not a nice word, very bad one, or let's say mediocre one, because 200 students is a lot, could understand something, and good ones asked questions, and he gave out exercises, and it was completely beautifully built up lecture, a 1-year lecture. And then I actually decided to become a mathematician. Until that it was just by chance I got there, but then I decided then I might try. Now, so therefore analytic number theory was always in my head, but never did anything. Zero, absolutely zero in analytic number theory.
I have counter examples to the statement.
Then please send me references. Yes, I promise that, or send it to Anna, because she is the one who, of course, reads the emails. Maybe also she is the one who explains me the proofs. Just answering your question, I sit in a very high-level class, analytic number theory, but introductory for graduate student. And then there was a beautiful proof, and then the professor who gave is one of the great number theorists. I will not tell the name for obvious reasons, and then he really talked about a very important result in analytic number theory. Now, I didn't understand completely the whole proof because it involved things which I did not know well, but at the very end, then he actually stopped when he arrived to the punchline. Then without it, everybody who is working on analytic number theory would have done. But now here comes the punchline that makes really the theory strong, and that is what moves the whole thing and proves the theory. And then I realized actually that was a kind of combinatorial idea, which if you give just independently to a combinatory, then would have solved it within a very finite time. So this is, I have this strong belief, though I cannot prove my cannot prove that my belief is valid, that in this so-called high-level mathematics, they have all the language, they develop theory, but many times actually they hide. Then at the heart of the proof actually there is a not combinatorics but combinatorial idea. Even at that institute there is a famous one who actually I consider as a god. I mean, unbelievable. That's just not only magicians, much more than that. And then, of course, he knows everything. He really knows in a broad spectrum of mathematics. But many of these proofs actually boils down to a combinatorial idea. So now this is, so that now the combinatorics is a little bit considered a more serious subject. Now, even the mathematicians who are working on some other much better established area start to understand that at some point even their results contain, a very huge part of the result contains a combinatorial, let's call it just combinatorial-like ideas. And I strongly believe it, though I just started to study some other part of mathematics, and this is the case. So it's a two-way street, most probably.
Combinatorial ideas or combinatorial-like ideas that you are talking about were in the heart of many results in continuous pure mathematics. Analytic number theory is particularly excellent examples because also Hardy and Littlewood used it and many others used it all the time. Now, these were the purest of the pure in the turn of the 20th century. This was the purest math you could do. In some sense, this was revered, this kind of mathematics. And despite the fact that this kind of mathematics was revered, and despite the fact that there were combinatorial ideas in many of the results, of course hidden at the time, combinatorics, which was used, in fact, also in sieving, right? Sieving for prime. What is it if not combinatorics, pure combinatorics, was not recognized somehow by the same mathematical community who maybe admired the analytic number theory and the results of what was produced. So how do you explain this this dichotomy? I mean, why wasn't it clear as it is clear now that combinatorics is an essential part of doing some and achieving many mathematical results? And we should, rather than push it down, we should, we should teach our students more of it. We should accept it. We should hire combinatorialists. Why was it like that 50 years ago?
This is just a guess. Not really a precise answer, at least I don't consider it as one, that there was no combinatorics by its own right practically, yes, before the, let's say, Second World War. Yeah. There was no such a thing, very few, like even in graph theory, which is a small part of discrete mathematics, combinatorics, the first results were done in the 40s. So maybe that is the reason then combinatorics as such did not exist. So then this mathematician didn't consider, didn't look after their own work as something which is of combinatorial nature.
But once it was created, let's say in the 60s,
I don't want to be too harsh on them.
this is your opportunity.
So I would say then some arrogance was involved in it. Then they looked down the combinatorics, maybe because that part was clear, then you didn't really need it, at least in the 60s. Now it's completely different, a lot of knowledge. And then they, of course, couldn't understand the difficulty and then why these people are just asking problem after problem. So somehow they admired the theory, as they wanted to build a theory and then use the theory to prove problems. So therefore they were not interested in combinatorics, just problems. But they didn't realize, most probably when in the 60s, then in combinatorics it's a little bit different. We usually start with a problem, but most probably what they missed, then by solving the problem you develop method and even theories. So then that part actually was missing for them, because already they had the judgments, and this is just a branch of problems as opposed to their a deep understanding of mathematics or maybe the universe and different and then theories and so on, which is extremely important. Let's not be mistaken. They are great mathematicians, this is great mathematics, but actually Tim Govers writes about these two things, and two cultures, the theory building and the problem solving. I do believe then this is now I hope that many others share my opinion, that is slightly artificial, because there is a real interplay, and that is how it should be. So I am very happy, even though I know only one part of it, if I know just a small part of discrete mathematics. But the reason is there was no combinatorics, just really answering your question. There's a field in the 20s, 30s, and so on.
It's probably also because just the ease at which you can generate problems. Possible also that lots of problems were not interesting, or the examples that many people saw were certainly not motivated. So if you either see the beauty of a painting in the museum and your friend thinks it's junk. So, and there just seemed to be an abundance of problems that many people were trying to solve without clear direction. But maybe this is how it had to develop initially. So out of these huge collections of problems, luckily many of them good ones, like the ones that Erdős generated, methods started to be developed. So, and by now I would say that we have even a few theories or larger understandings in combinatorics. What do you count as general methods in combinatorics?
General methods, like they started to use linear algebra, that is for me one of the most striking and hard problems, and suddenly like this magically, so that is method already that you systematically
for extremal set theory or extremal,
almost your first thought is that now let's try linear algebra or linear programming, or maybe semi-definite programming. So that was one area, at least to me actually, and also harmonical analysis. So harmonical analysis plays a big role, and then alone it's methods can be developed which are just, it's a method in harmonical analysis or a method in combinatorics, one cannot tell. Maybe it's a method in both. At least in arithmetic combinatorics, this is the case. This is the narrow subject which I know better. And then you know in theoretical computer science is that then yes, there are also the linear algebra is extremely powerful.
So what about more elementary methods that, I mean, like combinatorialists would develop by combinatorial means, so the probabilistic method?
The probabilistic method is maybe the best example in both theoretical computer science and combinatories. And then maybe one of the striking problem is the problem of the Ramsey numbers.
Can you explain it?
Maybe. So it will be a little bit technical, but that was most probably the most striking example of using the so-called probabilistic method. At that time, it was not method yet. It was just an idea, and it was Erdős' idea, though I have to tell them he was not the first one who used the probabilistic argument, proving deterministic results. The Ramsey problem is the following, that you have a complete graph and you two-color it.
The edges.
The edges. You two-color the edges, and then you want to find a monochromatic subgraph, which means then the subset of the vertex set, so that every two vertices in that subset has the same color. Maybe all of them are red or all of them are blue. And then let's assume that you have a graph on n vertices, so how big is the largest monochromatic? And then this is a relatively easy proof, then it should be at least log n, but then maybe it is much bigger. And then came Erdős, Paul Erdős, who in the 40s just randomly took color, meaning then, okay, took an edge, flipped a coin, and with probably one half it was red and half it was blue. And then he proved that for most of these choices, of a sequence of choices, which will result in coloring, there is no bigger monochromatic subset that I don't remember, I guess two times log n. Of course, still between log n and 2 log n, there is a
between 2 log n and half log n.
Yes, half log n, there is a gap, and this is one of the greatest unsolved problem in combinatorics, but definitely in graph theory, to close the gap. And then we really haven't made practically any progress in the last 50 years.
There are two things about this probabilistic method. Of course, it became one of the major tools in combinatorics, and it has books and great applications. Two developments out of it. One, that it started being refined, and you mentioned before, I think, the semi-random method. So maybe you can give an example of what this is.
Actually, this is very strange that we developed this, let's call it now method, though for a very long time they didn't call it a method, it was just buried in a obscure paper, not obscure journal, but obscure paper. It was a journal, a European Journal of Combinatorics. And then actually what we wanted to construct a dense infinite Sidon sequence. For a long time it was an open problem. Still there is no complete solution, but at least that was the first step.
So a Sidon sequence is a set which does not contain any of the differences.
Right, so any
elements.
two differences is different. Yes, that is a Sidon sequence, and then up to n how many you can have. Always it is easy to prove, then if you just randomly choose an n to the 1/3 you have. But whether you can have more, of course, you cannot have more than n to the 1/2, because then just by the volume argument, or I don't know which one, or principle, whatever, it's easy to prove. But n to the 1/3 was for a very long time, for 40 years, the best.
N to the 1/3 means there are, if you pick randomly n to the 1/3 integers between 1 and n, no difference will be
right,
contained.
And then you can continue it up, so it will, the whole problem is for infinite, because for finite and there were a construction, then square root n elements, but this is just a finite set. But the problem was an infinite, and then of course there is an interplay between the elements, and then we constructed where for every n we had at least n to the 1/3 times log n elements. And for that, we needed this, let's call it lemma, which by our opinion, but this is only our opinion, started the so-called pseudo-random method, that to run theorem states the following, that you have a graph on n vertices so that the maximum degree is d, then you have always an independent set of size n over d. And of course, you cannot improve it because you have a common union of complete graphs on the vertices, then this is it.
Yeah.
Every degree is d, and then, of course, from every complete graph you can choose only one point. But then we started to meditate what is the reason why Turan theorem is such as. And then we realized if the number of triangles, not that much, but a little bit less than that, then actually you can prove something more.
You don't allow complete graphs by disallowing even having just a few triangles.
Right,
Or let's
so
say no
well, you
triangles.
count then how many triangles you have in this case, and then if you have much less, let's say no triangle in the extreme case, yes, because in this complete graph a lot of triangles you have, then the largest independent set is n over d times log d, and this is exact. So you can gain a little bit, but log d, and it was important to gain this log d, and even we could improve it then if you have a graph where the number of triangles is smaller than in this example, then it's more than n over d. It's n over d times some multiplied by something which tends to infinity and tends to the infinity.
So what is semi-random?
So the
you don't
randomly you half, so you just choose half of the points. That is, and then in the one half you find an independent set which is of n over d. But in the another half, so if you choose it randomly, then the another half, all the properties will be maintained, so the right degree. Then you choose against the half
So the
randomly.
degree goes down and...
Yes, but in a nice way, so because you choose it randomly. But once you have a random round, then in the graph, then you by hand you choose the largest independent set that is not random, and then again half it randomly and then choose an independent set, and of course put it together, then you will get a bigger independent set. So that is a mixture of randomness and deterministic random argument and determinist argument, so that is why we called it pseudo-random method.
The other question about probabilistic arguments, whether completely random or semi-random or any, is that it's very powerful to prove the existence of objects or with certain properties, but it doesn't tell you where they are. So you just don't. It's not completely satisfactory, in that often you would like to know you know where is the object you are looking for. If you don't have randomness, if you let's say construct a good Ramsey graph, construct a two-coloring which does not have large monochromatic subsets. So the probabilistic method, I mean, at least I personally don't find it completely satisfactory, and there are many problems for which getting a deterministic solution of a similar quality will be extremely important. So in particular, proving that certain problems are hard. We know that random problems are difficult. This is an application of the probabilistic method, usually, and we don't know how to exhibit hard problems. So the question is, I mean, maybe it's some intuition you have. I know you thought about some of these problems. Why is constructing such objects difficult when we know that almost all of them are of the type we like?
Let's go back to the Ramsey number and co-authors. Ramsey number, then Erdős's proof was probabilistic, but nobody could give a concrete two-coloring of the graph so that there was no I guess at the very beginning square root 10, monochromatic square root 10. Definitely if we wanted a bipartite monochromatic, square root 10 was for a very long time the best. And then the theoretical computer scientists came up and completely defeated the combinatories, because now I guess your best bound is not log n, yes, the best possible, but very close to it, yes, it's log n to the, what is the bound?
It's 2 to the square root of log n or something like that. So
Yes,
it's not a polylog, but it's much less than.
Poor combinatories never would have come even close to these things. So it actually required, also it was the proof, of course, contained a lot of combinatorial.
In particular, this this Burgen-Katz-Tower result on some product.
Right, yes. But nevertheless, it needed, if we might formulate it, that a way of thinking how the theoretical computer science, even when they think about combinatorics, I believe then they look at it a little bit differently than, for instance, I would look at it.
Maybe we are more liberal in that we allow ourselves any algorithm to generate the object we want, as opposed to just asking for it to be a polynomial, which is a more mathematical thing. But still, so of course there are examples where there are explicit constructions of objects. Expanders are another beautiful example. But the most interesting problem to me is P versus NP, or more generally proving that some natural problems are difficult. And we cannot do a single example of this, even when we are limiting what we call hard to something which is almost completely trivial. The usual way to phrase these questions is about constructing an object. You can ask any mathematicians, any high school student almost, to find a matrix. So not only does it have high rank, but also if you change just a few of the entries, 1/1,000,000 of the entries, it remains high rank. A random matrix has this property. This is true over any field you want. And yeah, I guess you can answer, you don't know why this should be hard, but it seems that combinatorics solve much harder problems.
Seems, but may not be the truth, because maybe then this is really, for some reason, it's a very, very deep problem. So there must be some reason then so many strong theoretical computer scientists and even mathematicians have been working on it. For me, this is a good enough explanation. Then so much energy has been devoted to solve this problem. It's a beautiful problem. It's one of my favorite problems. I tried without absolutely any success, and well, you had and your group some success, but yes, the problem is still open. No, this is very, very hard, and I am not sure that this is combinatorial by nature. Actually, once we are here, you were the one who told me this problem. And this is my plan, but maybe by the time I will...
That's one of the problems you didn't mention that you are going to work on.
Yeah, right.
Okay, now it's out. Yeah.
Okay. So you should be, how do you call the ones who are searching for the secret of others? Okay, that is one of the problems. The another one is almost not the same, but this, in some sense close. You know this problem, and this is really shame. And then if we have a circuit which the depth is log n and the size is linear, that give a concrete Boolean function which cannot be computed with such an animal. Yeah. That is one of my favorite, and that is actually our common shape, both for the combinatorics community and the theoretical computer science community. Even the first step. Yeah. This is like in Hilbert problem for the 4 points. Even the third step is not done in that direction. But it's a beautiful, beautiful problem, and who knows, in 5 years, because now a lot of other methods came into the place, so maybe.
This is one of the results with you had with Aytay and Komlos.
Yes.
So this collaboration is legendary. I mean, I don't know how many papers you wrote together, 20, 30, some of the hardest problems that people tried and failed for a long time, the three of you solved. So I was curious about this collaboration. I know the three of you. I mean, you were all in Hungary at the time.
Right.
And you're very different. You have very different styles of work, and in fact, I would say, let's say, between Aytay and yourself, there's even a gap in sort of interest or in motivation and the problems that he's looking at. So I was wondering how the chemistry worked. You obviously had a fantastic chemistry. You worked really well together. So did you meet and?
Yeah, we met. And then I guess the deepest mathematician of three of us is Miki Aytay, and then Komlos is extremely fast, and I have sometimes some contribution.
You made the coffee, I'm sure.
But the coffee they didn't like.
Choosing the problems was an issue even.
Choosing the problem, I spent some time at Stanford in the 70s, 74. Donald Knuth the Great, as the computer scientist, invited me. I guess Ron Graham arranged the invitation, and there I heard the problem and I went back to Hungary.
One problem, but no, in general, I mean, there were many problems that, there were computer science problems, of course, yes, like the sorting network or the de-randomization. Oh, the sorting network you heard from the de-randomization, but also lots of, just combinatorial problems that...
It's not so much, so many combinatorial problems, maybe 5.
How long did it last, this collaboration?
It's, well, Miki left the country in 82, and practically it lasted until 82, because then Miki went to the IBM San Jose Almaden Research Center, and then we mainly stayed in Hungary. Komlos then came to San Diego, and then so we were separated, and practically that was the end because of the physical design. In Budapest we talked to each other. We went to maybe Miki's house, and then in the garden we talked, and also we worked in the same institute, in the Rényi Institute, so physically it was completely different.
You talked about being a graduate student in Budapest and working with Erdős and Sarkozy, and then you went to Russia. Was this common for Hungarian students?
Yes, so we have a system in Hungary. I guess not only in Hungary, but in the, let's call it now for simplicity, the Eastern Bloc, which includes Czechoslovakia. At that time it was called, and then Poland, and so on, Bulgaria, Romania, and so on. So you finished the university, and then you could write a dissertation which was called the doctorate of the university. But this was not on the level of the PhD. Here it is not equivalent. It was simpler. And then the next one was the candidate of science, candidate of mathematics. That was more or less equivalent to the PhD. In some sense stronger, in some sense weaker. That's just the reason it was equivalent. And then sometimes you went abroad. For instance, in mathematics, Moscow was a natural choice because we had connections only at most Eastern Eastern Germany and then Poland and then Russia. So mostly, of course, because the Russian mathematics was even at that time at the top. So they always, and historically, the Russian mathematics has always been extremely strong. So many meant as a candidate. So it means that you study 3 years, just like PhD, and then you write a dissertation, and then you become a candidate of science. So it was very common to do this. Or you could stay in Hungary and do the same thing, 3-year study, and then write a dissertation. But I decided to go to Moscow because exactly my bad consciousness. So I realized that I have to study something. And then I went to Moscow I even remember I was 27 at that time, so in 67 I went to Russia, and then you have to apply, you have to fill papers. Actually, you had to also pass Russian exam. I failed twice, but third times I somehow got through, and then I could go to Russia. But I ended up with Gelfand, who was a great mathematician, but he works on Israel Moisevich Gelfand. He works on completely different subjects, very abstract for me. May not be abstract if I knew the material, if I had the background, then it would have been maybe completely perfect for me. But in fact, I wanted, as I told you, to study number theory. Right. And actually, at this university in Moscow, the main university, the one who worked on analytic numbers was Gelfand.
So it's a one character difference.
One character difference. Now you see, a lot of things can make a difference in your life, but that is a little bit annoying if one character makes a difference.
There is a wonderful Asimov story called Spell My Name with an S, where a person who suffers is advised to change the spelling of his name by one letter, and it indeed changes his life. So this is a reality. It's not just a novel in your case.
That is a fiction, right?
Yeah.
Asimov. So mine is a true story. So I wrote Gelfand. And also because it had to be written, and I use my right hand because at that time I started elementary school in 46, and at that time still the culture was that you had to learn to write with your right hand. And I am I am completely left-handed, and also when I play soccer, then I used my left hand. I am completely left-handed, so nevertheless, so maybe this is the reason why my A look like my O, or my O look like A. I don't know. So definitely, so I ended up with Gelfand, and which is very and this one letter was a big difference because Gelfand was a small guy and Gelfand was a giant. But I only realized it when I arrived to Moscow, and it was very hard to change because the system was not very rigid, not very flexible, and it was a little bit, strange. You have the privilege to work with Israel Moisevich Gelfand. What else you need? Actually, what you need not to work with with Gelfand. So I remember the first meet with Gelfand because we were introduced when we arrived. He didn't know that I didn't know anything, so he just asked a question, my age.
So he asked your age?
He asked my age, and then I told him that I am 27. It was 67. He said, okay, this is too old. And so choose some other profession. There are so many other good professions. Of course, he had the reason because he had all these superstar students, Margulis, Kazhdan, even his son. Yes, and his son was good. And a lot of who were 20 or 21, also Bernstein. So of course, he had the reason to believe that 27, if you want to start, because they already knew that they were superstar.
A great beginning. He told you you are too old, and what happened?
Yeah, that was a great beginning, and I was not surprised. If you see that somebody is extremely, I knew that he is great in something, then you assume, sometimes without any justification, then that person is right with almost everything, not with everything, but also maybe he was right in this with high probability. So I meditated a little bit, but I am a coward, so I didn't want to change, because then you have to write to the Hungarian authorities and so on and so on. So I stayed with Gelfand.
So did you work with him at all? Did you talk to him because
he realized that I didn't have the background, not even this, because even I didn't have the background in analytic numbers, which is much closer to my taste and most probably to my ability to learn. No, he first told to Kazhdan to talk to me, but Kazhdan is exactly only immediately realized, and we talked with many other things. He has a very broad interest in other aspects of life. Yeah. And then finally his wife, very nice lady, started to teach me elementary analysis, calculus practically. So that was all, but I would never talked with Israel Mosevich Gelfand about mathematics. We actually talk about paintings, because I had a friend who was a student of Gelfand, and he was a very well educated and very good at judging art. Mm-hmm. And then I always went with him to Gelfand's apartment, so Gelfand sometimes asked me. And actually there is a story which is strange but true. That once he left me alone because he had to run somewhere else, and he had on the wall these very strange abstract paintings. Mm-hmm. And then I went much closer to the paintings, and I could read when the artist painted the paintings. And so there are, let's say 10 abstract paintings, and then let you imagine you are asked the opinion. Of course, from some distance they look all the same. Yeah. Actually, even if you go closer, they are still the same. Actually, what I learned from my daughters who care about my education now, and for instance, if Rothko's picture, you have to look at some distance, mm-hmm. very close to the. Then you establish an emotional connection between yourself and the painting. So, but whatever. Right, of course. Daughters are daughters. So, but in this case, I remember the dates, and then I next time I didn't see anything. But when because he liked this painter, it was his favorite painter. I don't know his name. Most probably at that time he was in Russia, a very recognized painter. Gelfand actually had a very good taste, and he knew. So these Russians had the classical education, so they really were good in many things, music and art and written. So then he asked at some point my opinion by chance. I am not sure whether he was really interested or it was just a routine question. Mm-hmm. But then I started to give a lecture, kind of lecture. Then, okay, at that picture, I am not sure, but it seems to be then the painter doesn't have the full, so all the tools, so technically, but some freshness, I feel, energy. And then as we go further because on the right to the left, the time is passing. Absolutely, now you see, it's in full strength, and then later somehow technique is still there, but you don't feel this energy. So after that, I was saved. So all what we did, then we exchanged.
He was amazed.
He was that he, of course, rightfully didn't assume that I am an expert on art, but didn't question the reason, of course, why he just. So after that, we presented to each other art books. He icons he presented, and at that time in Russia you couldn't buy a book about a painter like Leonardo, whatever, or Bosch. He liked Bosch very much. In Hungary, yes, we had a like Risoli. They have a sequence for each painter, yes, a book. And so I presented to Gelfand. Actually, I later developed it a little bit further, so I became kind of a not really smuggler, but I took 10 books, and because I took the train is 1.5 days from Budapest to Moscow, and then I studied. And then strangely enough, although the Russian books were very cheap, but these ones, because they were printed on a white paper which they couldn't reproduce, so you could sell it for a very good price. So somehow, luckily, the interest in art and the financial advantage worked aligned, yes. So my dissertation was about combinatorics. Actually, four-term arithmetic progression was one of them.
This was done in Moscow.
Not done, but a little bit earlier, but he let. So you could write the dissertation up to that point if it has not appeared yet, and then he let me to do this and two other results which I don't exactly remember. But one thing I remember then I had to pass an exam, so you have to do two things: present your dissertation and pass the exam. And the exam was about representation theory. And actually, and the subject was, and just two exercises from the first grade book. Kirillov wrote a book on represent. I guess Kirillov is now in US, United States, maybe in Philadelphia or somewhere close to here. And then I solved two problems, and also Bernstein, a very nice person and a great mathematician, was the one, Joseph, yes, Bernstein.
He was younger than you, no?
Much younger, it's 6 years younger.
Oh, but he was your examiner.
He actually checked my solution. Oh, well, there was, of course, none of the solution was correct, but he said that, well, it's not what really counts then whether the solution is good, that how much energy I put into it. So he was very nice. So I passed the exam, and then I had to present at the so-called Gelfand seminar, which is a world-famous seminar. All these extremely strong Russian mathematicians, or many of them, were present at that time, and then you had to present your dissertation. In general, you had to present, there were always a speaker, and it was 4 hours long. These were long seminars. And I remember that whoever was was giving the talk, then Gelfand always went to the board, erased everything, then this is foolish, and this is how it should be done.
There are lots of stories about this.
Yeah, that was a standard. I remember there was only one guy who protested. It was Novikov, who is also in US now, the mathematical physicist, this big shot Fields medalist. And that strong guy, obviously strong character.
He protested when
yeah, he said, okay, look, if you want to give a talk, I am not against it. Of course, I'm not going to sit here because I have something else to do then, but so he was the only one.
How did Gelfand react to this?
The effect was stunning. He let Novikov to say continue, wow. Yes, without any interruption. So, but he was Novikov, he was not me. When I presented my result, in every 10 minutes, some of these big shots stood up, went to the board, and said, fine, stop for a minute. Now I give a proof, which is much simpler than yours. Okay. And I worked on this problem for a while, and then he gave the proof. Then I said fine, so there are now 2 proofs, and then and solved. So this result had, by the end of the of this presentation, had 10 different proofs.
This was a four-term arithmetic progression.
Four-term arithmetic.
They simplified,
No. They give a completely new proof of the same result. Yes. So of course, none of them was good. I didn't want to point out the basic error, which actually everybody who is in combinatorics immediately would have told them, but I didn't consider it as a competition for publishing. So I was sure of that. So I just let them to have their own proof. And that was it. But eventually, well, my proof was at least the first one. So therefore, I passed this exam too.
You talked at the Gelfand seminar about your work on the four-term arithmetic progression. So maybe you should explain the van der Waerden theorem and the Erdős-Turan conjecture and the Semredy theorem, I guess.
So van der Waerden theorem states the following: then you fix two integers k and l, and then choose a large integer n, and then you partition into R classes the integers from 1 to n. Then van der Waerden theorem states that in one class always there will be k numbers which form an arithmetic progression. That is van der Waerden theorem. So it's a beautiful theorem.
No matter how you partition a very large set of consecutive integers into a small number of classes, one of the classes will always have a long arithmetic progression.
That's right. If I could really formulate things properly, yes, that would be the formulation. Yes.
So that was a theorem.
Yes.
By the way, this theorem, did you know of it before?
Yes,
it was, yeah. So this was something you considered a good problem to solve for van der Waerden?
No, I knew van der Waerden theorem. And then what really happened is that, because I knew van der Waerden theorem, I assumed a lot of things are true. And what I really wanted to prove is that if you have an arithmetic progression, it cannot be that positive percentage of the elements are square numbers. That is what I really wanted to prove. So how I proved it, there was two parts to it. The first part was then if you have a positive percentage of the numbers in an arithmetic progression, then always this set will contain 4 elements which forms an arithmetic progression. It's a 4-term arithmetic progression.
This is a positive percentage of integers.
Yes, of this arithmetic progression, positive percentage of the integers in this arithmetic progressions. Then I said, okay, fine, it is clear, then there are 4 which forms an arithmetic progression. And then, so that was easy, I just assumed, and this is true, everybody should know this. And then the second part of the proof was that if you have 4 integers which forms an arithmetic progression, then it cannot be then all of them are square numbers, and that would have, of course, proved the whole theorem. And I was very proud. Usually I am not proud of my results in mathematics, and at that time also I was young, this was before Moscow, and I went to Erdős. I went to Erdős if I thought that I did something which is of some value. Then I told him I was extremely happy that, look, I proved this one. It was not, I don't want extremely famous problem, but definitely it was considered to be a difficult problem. Mm-hmm. And then Erdős told me that there are 2 small problems with the proof. namely then your assumptions might be true, but nobody proved so far.
The
Four-term arithmetic progression, it is not known. Nevertheless, and then the second part, which was actually a little bit more embarrassing, that it was already proved by Euler, like 250 years ago. So the part which I assumed was not proved, to be true was not proved, and the second one has been proved 250 years ago. So you cannot imagine a worse situation. You obviously, I should have followed Gelfand's advice, but at that time I didn't know his advice. Yes, it was 2 or 3 years earlier, so I just didn't change my profession. Still, well, I said, I was a little bit sad for 2-3 days, but then I said, okay, well, once you got this lecture, then why not to start with the arithmetic progression, which was not proved by Euler, of course, if it was not known. So
this problem was not a famous problem at the time because it was there, the Sturran question, right?
Yes, but the problem that if you have an arithmetic progression, then positive percentage cannot be squared, it was also a serious problem.
Yeah.
So it was would have been my most serious result up to that time.
Yeah, no, I'm asking if you didn't know about the other problem, about the Erdős-Sturran.
No, if I knew that,
okay.
Well,
it was,
that
I guess
would
you
be,
didn't, yeah.
Then for sure Gelfand would have been right, yes, to choose as a profession, yes, if I knew that.
Erdős told you actually that it was a question that he was
yes. Because I knew van der Waarden's theorem, yes, then if you color. Yeah. So therefore, most I assume that of course then you have a big enough set, then it already contains arbitrary long arithmetic progression.
So this is exactly the problem.
This is exactly. So this is exactly the problem. So what now was open, then if you have positive percentage of the integers up to n, then it contains an arithmetic progression of strength 4. Of course, for 3 it was already Roth's result.
But this you knew, the Roth result at the time, for example? Or like before, or you didn't, this was not a problem you cared about till then?
No, I might have heard that, I don't know. But then escaped my attention. And beside this, Roth gave a bound. So maybe that is why I overlooked then for 4. I haven't heard then somebody. Anyway, I assumed, and then I started work on the 4-term arithmetic progression exactly because of this very bad experiment. And after a while, I solved it.
So this was a long time, but after a while, how long did it take to solve?
It didn't take too much, actually. It didn't take too much. It was such that I said it was maybe in 66, and then Erdős arranged a visit to Nottingham in England. Mm-hmm. And I had to give a lecture on this so-called solution. At that time it was not clear then the solution was right because I didn't explain it to anybody. And then I had to give a series of lectures. They asked me because they were interested in it.
The number theorists were interested in it.
Wiersing and Elliot was there. They are number theorists, famous number theorists. And then I started, but my English was not really good. Even now you could actually judge, and after having spent 20 years in the States, my English is still... could be improved, just to say. So anyway, at that time it was non-existing. I can tell you the story even later how I learned English. So I, on the board, just draw pictures and I say meditation show. That was all what I said. That was all the explanation. A picture and then meditation shows. And so many times. So it's my pronunciation, at least of that sentence, were getting better and better and better. And more convincing. So actually, I didn't say it louder, always the same tone. But they were very clever, and from the picture, and maybe I added a little bit more, so it's an exaggeration a little bit. So they understood the proof and they wrote it down for me. They were very nice. So the result, and they checked, and it was correct, and they wrote it down. So I am extremely grateful to Peter Elliott and Edward Wirsing. It was a real great help.
So, but let me understand about this, because about just this proof of the four-term arithmetic progression. You knew, anyway, you started working on it, and you knew that for 3 it was known. I mean, if you have a positive percentage, then there is a 3-term. Now, this Roth proof is a proof by Fourier analysis.
Right.
Your proof for 4 is by combinatorial methods. So, elementary combinatorial method. So, did you try to extend the Fourier analytic method?
I was uneasy with mathematics in general. So Fourier analysis, though it was not really a hard Fourier analysis, so it's not what a real mathematician who really works on Fourier analysis would call it hard stuff. It was actually relatively easy stuff. I could have learned it for sure. But because it was not in my vein, so...
So did you prove first the 3-term arithmetic progression?
I gave for the 3-term a completely different proof of everything, where I used the so-called high Hilbert cube. And it turned out to be the case that now this Tim Gowers project, the Hales Dewey, they also use this Hilbert cube, and they inducted on Hilbert cube. Maybe that's not clear, most probably it's not true, but if I inducted later on the Hilbert cube, I could have got the Hales Dewey. Yeah. But of course there are some other ideas, but definitely I did not do this. But that the 3-term arithmetic progression I used proved using the Hilbert cube. And this is even in the book of Ron Graham, Spencer, and Rothschild.
On the Ramsey theory.
Yes, on the Ramsey theory. And then I tried to prove the R4. I proved reasonably fast, 2-3 months at most. And I went to Nottingham, then they really helped to write me, not help me write, they wrote it up, yes, so it's, no, but of course based partially, let's say it, on my explanation. And then I went home, and then I went to Moscow. And then I haven't worked on RKN until I came back from Moscow. So,
but I mean, just when you solved R4, did you see that R5 is different nature?
Yes, I did see that it requires much more work already. So between 4 and 5 there is a jump, most probably much bigger jump than between 3 and 4. And then you can see it from Gowers' beautiful and absolutely groundbreaking proof, and the real jump from 4 to 5, but of course then from 5 to K it's many new ideas in Gowers' proof, which actually changed the landscape almost completely. But it was something like 25 or maybe 30 years later. So after R4 I stopped working on this and went to Moscow. After coming back to Moscow, then I started with in 72 I started to work, and about 3-4 months I proved. So it took a long time, mainly because I didn't work on it. Maybe if I worked on it the whole time, I couldn't have proved it. So maybe, well, you know this phenomenon. Then you come back to the problem later, and then you somehow, by chance, solve the problem, or just got an idea, maybe sometimes out of blue, or step by step you improve, you start to understand the problem and prove it.
already in the four-term arithmetic progression, you used graphs. You used you reduce the problem to basically a problem about graphs, and at least for the general solution, you need to use what is everybody called the celebrated Semeredi regularity lemma. Can you explain the lemma?
Actually, in this RKN, there was no regularity lemma at all.
In
RKN, there was no regularity lemma at all. There was something which was similar, much more complicated, definitely not the regularity lemma. But now people say that there are so many different regularity lemmas. Many of them are much stronger. Actually, all of them are stronger than mine. Mine was just the beginning. The real regularity lemma, and then people generalized and then simplified and so on. But definitely in the original paper, there was something where maybe you could detect the idea or notation or something, but definitely not the regularity lemma, as I maybe in 5 minutes will formulate something, but completely different.
It's completely different, but it's of the same nature, of a
Yes,
nature.
yes, that actually, if you really analyze, but to almost every, it's like exaggeration again, to two different things actually, eventually you can come to the conclusion that they are of the same in some sense.
So maybe you describe the lemma, and then I'll ask you about the other lemma, how it
Which
compares.
I don't know because it is complicated, so that is why I don't remember this lemma. But when I heard it, then I checked it and I said, okay, it's a different thing, but still I couldn't convince anybody.
So this is your opportunity to set the record straight and say what was in which paper of yours.
Right. In this paper, there was, by my opinion, but maybe this is only my opinion, no regularity lemma, something which is similar to that in some sense, but in graph theory, a lot of things are similar to each. There was something similar, and then once I have the opinion, I would like to say that actually now the same story repeated itself, namely that I told the solution to my good friend András Hajnal, and after the RK solution, and he listened. I had a note actually, so I computed everything, except I still didn't know English, and also my lectures at that time, even now, are not really something which you would give an example how to give a good lecture. So, but András is my good friend, and then also we drink a little bit while he was writing up. So the wife actually wished then the paper was a little bit shorter. So András wrote it up, and then and again I would like to thank him for his extremely great help. And then it appeared in Acta Arithmetica in 1975. And then in 1974, I heard a lecture given by Bolobás about the Erdős-Stone problem. And I don't want, this was actually an interesting result from the 40s. But some magnitude was not correct. And then Béla talked about this, and I wanted to improve it so that to get the sharp results. And actually for this problem was the regularity lemma done. So I needed I felt then the regularity lemma, and then suddenly it came to my mind, and this is, you can formulate a much simpler lemma than what was in the RKN, and even the proof is simpler. And then once I proved it, that with and then the same story of course repeats itself. My good friend Vasek Svatal wrote it up. And later we had a joint paper about the Erdős-Stone, the application of the regularity lemma. So that is the real story. Now people can say I am wrong, it was there, but it was not there. The regularity lemma itself appeared separately in some conference volumes, so I can prove this, that at least I didn't understand and then what was in the original paper.
But you could see that the new regularity lemma could be used also in the proof for the RK.
Yes,
So
of course, it's
it
much
was
stronger.
simpler and
It's
stronger, yeah.
stringer and
Okay,
stronger.
so maybe you can describe it,
Yes,
regularity lemma.
well, the regularity lemma basically says that if you have a graph, let's say dense graph, so a lot of edges, then you can break the vertex set into a reasonably small number, so you can partition the vertex set into reasonably small number of classes.
Constant,
independent of n, which
graph.
is extremely important.
Yeah.
Then if you just tell me then what precision you want, and then based on it you can determine then how many classes are in the partition. And then you can partition the vertex set so that I am not going to tell the exact result, but almost every pair of classes, if you between them you consider the edges, that is called a bipartite graph, then this is regular, which means then there is a density between these two vertex set. The density is nothing else the number of edges divided by the V1 and the size of the first set and the size of the second set.
What fraction of the total number of edges?
Yes, exactly. The fraction of, if it was a complete graph, yes, what fraction. And then if you take two, regardless how you take two reasonably big subset, epsilon percentage of the vertex set up and the vertex set down, then between them the graph still will have practically the same density.
So it is a property that a random graph would have.
Exactly. So the regularity lemma is actually kind of a philosophical statement. It's not hard to prove the regularity lemma. So it's really not such a big deal. It just says that if you have a graph that there is no total chaos, you can break it into relatively small number of classes, so that these classes and the bipartite graphs are random, and we all know we are working on this probability things, then there is nothing nicer than the random graph. The random graph has all the nice properties. So then the regularity lemma states that you can break the graph into pieces, not too many pieces, so that the resulting bipartite graphs have all the nice properties. So everything is, so that is why I call the whole graph is a chaos, because you just don't know what are the edges. But then you can break it down so with big pieces, so that there is a almost total order.
I would agree with you that it's not very difficult to prove it, but to think of it, I mean, it's actually, it's one of the most amazing things, I think, that I know in mathematics. So to think of it, it's in some sense much stronger than a Ramsey theorem. You can also interpret as that every chaos there is order, but there the order is tiny. You find a really, really tiny piece of the graph where there is fantastic order. They are all red or all blue. Here you take the graph, and essentially all of it is ordered if you work a little to organize the order. So it's just a few parts. So maybe the graph is not a random graph, or does not look like a random graph. But if you just look at 10% of the vertices here and 10% here and how they talk to each other, essentially all of these are random. I think it's sort of amazing to expect that something so strong would be true. Very counterintuitive. So was it clear to you that it should be there, or no?
No, I don't want to claim that when I start to do something, it's clear to me. I needed.
You wanted it to be true.
I want it to be true, yes. And it happened to be true. Yes, happened to be true. a lot of things is just Cauchy-Schwarz. Yes.
Of course, mathematics
is basically Fubinian Cauchy-Schwarz.
When you understood this, of course, you needed it for Erdős-Thon, let's say, or for a particular concrete reason. But at least I guess it was clear that it's an enormously powerful tool. That every graph can be, you know.
Then I realized it didn't take too much time to realize that it can be applied here or there. But I was just a graph theorist, and still mostly I am just a graph theorist. So, but in graph theory, in extremal graph theory, then I realized that it is powerful. And then it happened to be the case that this or the modification of it, generalization are even more powerful in many areas, like in theoretical computer science. But to my great surprise, actually, they apply it in biology and neuroscience in Hungary. I don't know how, but because that is a graph and some connections, and they break it into things which...
I mean, you just said that Cauchy-Schwarz is applied everywhere, and so maybe it's universal. I think the regularity lemma is an extremely universal. I mean, so this it says much strongly, I think, that in a completely unorganized system there is a very strong sense of order. Order in the sense that things are random or look random, but random, like you said, means we know we'll find what we expect as frequently as we expect it in a random graph. So it's not, I think, to me, and I think to combinatorics in general, this was the first major technique that exists. So there are lots of techniques or lots of methods used in combinatorics, but this was one of the first big hammers or universal tools that whenever you were faced with any problem, the first thing you'd say to yourself, wait a minute, let's assume that we partition it into regular pairs and then we work on them because they are much nicer. We know today that the regularity lemma is not a universal tool in combinatorics, but in mathematics. So, of course, Terry Tao popularized it to a large extent, and not, like you said, not just the theorem itself, but the philosophy behind it, that in large systems which are maybe of a different nature, in partial differential equations, other problems in analysis. It happens actually also in theoretical computer science and in for other structures, not just graphs, that we can take a very large and complicated object and just give a few bits of information about it, just partition it into a few parts, and then each part behave like it's random in the appropriate sense, and then we can analyze it much better. There was maybe 30 years in which this tool was used only in combinatorics, and then suddenly, this broke out. Either you think it's an accident, it's just a green Tau theorem.
It is maybe just luck, but it sometimes happens, and for 30 years nothing happens, and the marriage breaks up. No, I don't know why it happened. I consider myself lucky because I'm just working on problems here and there, and the others are the ones who realize and there is a connection, and then they apply and they develop much stronger results, and then they establish connection between these things. So this is not my role. I just got really lucky to solve this or that that. Maybe I could have solved some other 3 problems and without any influence whatsoever. But yes, this for 30 years, but in graph theory it was widely used. Yes. But you are absolutely right, and nowhere else. And then suddenly in the 95, already in computer science. So computer scientists were before Terry Tao and so on, yes, because property testing and then some algorithm already they used but definitely it was not earlier than the 90s, and then at least 25 years, 75, 15 years passed without without the fact that some other area of mathematics was interested in this lemma. But this lemma is just a universal statement. It's really a philosophy how to approach some kind of problems.
Yeah, but well, it must be extremely rewarding to see that it becomes a universal tool, with so many applications. I think it's a rare occurrence in, Cauchy Schwarz, okay, we agree, they did something that everybody used. Now the summary regularity lemma is, and the philosophy behind it, which is even more important, is something that is this dichotomy of structure and randomness is, so it must be fantastically rewarding.
But I am not against it, and they say that. Yes, I am happy that I did it. Well, just like everybody else would be happy. You are happy if you prove something, or...
You have to accept my word for it. It rarely happens that people discover something that is of use to, in such a wide context, become such a widely used tool. Maybe you can describe roughly where you moved, when did you first leave Hungary, where you lived, and how was it for the family?
First time, before I married Anna, I went to Stanford, and I could tell you the story how it happened. Actually, I met Anna before that, and then she invited and introduced to the parents, and then the main figure in the family was the Katineni, the mother of Anna. And then she escorted me. She knew that I was living for a long time. It was for 8 months or something like this. And then at that time, the air companies gave you a bag. And then she traveled a lot because of her profession. So she gave me this bag, she escorted to the door, and we told me, you don't have to return. So after that I married her daughter. With the family in 82 we went to Columbia, South Carolina. And that was a little bit harder because we took the children, they were still young, completely new, everything, and that was hard to adapt for them. And Anna can adapt to everything.
The children were too young to school, right?
Yes. No, 5 years, yes, preschool, but Andre and Anita was already in the elementary school and then the secondary school. And so it was not easy, then they told later, but the real thing was that I became very sick at that time. So we planned to spend then 1 year, but we had to spend 2 years because of my treatment. So therefore I cannot say that without it what would have been. But with it was a little bit tough. On the other hand, then the family was very close, and Katineni, the one who gave me the bag, she was a very nice lady, came to help. And then after that, when we really moved to Princeton, though I am not working at Princeton, I am at the computer science department at Rutgers University, which is also a somewhat strange story because I don't use computers, I never.
Me neither.
Yes, but you know a lot of things what to do with computer. No, you don't?
No, I don't.
You only just to read?
Yeah, I don't.
That I know.
I can read my email.
But nobody asked me as then whether I can switch on the computer, so they applied. At that time it was very fashionable, this theoretical computer science. So from 90 we came, and then
the kids were already in school, and
right.
So this was hard again, the switch from.
No, then after that, in 4 years later, but it was Princeton, which is a pretty snobbish place. And then they were a kind of outcast. They didn't tell it as only, at that time we only took the two daughters because the other two were already older, and then they stayed at home, so they visited quite often us. But then they said then they didn't feel at home at Princeton, but then they studied at Rutgers and they liked Rutgers because Rutgers is very diverse and somehow friendlier in that sense. So then they liked it. So for them by that time it became easy.
But that was a permanent move already. So I guess
Permanent because I have a permanent job at Rutgers still I have. After that everything became a little bit easier, but it is a big problem to move the children here. Their change for them most probably is even harder because you just cannot find new friends. We are mathematicians, we work on mathematics, we already more or less know the people from conferences or from other places, but for them always to find new friends it is very difficult, new style of maybe teaching, but also there is a benefit. Yes, they learn languages, they see something different. So this is a mixture of both good and bad. But personally, I like to stay in Hungary, and I am not afraid to say I just came for the money here because I am a combinatorist. Maybe it's the same reason. But sometimes people come because you can learn here a lot. But I was combinatorist, so I could have done exactly the same thing in Hungary, but of course the salary here is different and we have a lot of children, so that is the main reason actually why we are still here. So we are very grateful to this country because they really helped us materially, definitely financially. But if I could choose, I just would stay strictly in Hungary. And now we spend 9 months in Hungary and 3 months here.
Being in a computer science department is, does it matter to you?
Well, it doesn't matter in a sense that I am neglected. So I am a kind of, nobody really cares.
So they respect whatever research you do?
I teach, I have the same teaching load, but they didn't really tell me what to do. So in that case, they neglected me, and if I had an opinion, which I don't, because usually I don't say anything in the faculty meetings, then I am pretty sure that they wouldn't have listened to me. Once I tried just to check my theory. And yeah, I was right, yes. But this is actually a very comfortable position to be in. By the way, I had a choice at that time when I joined the Rutgers to go to the math department or the computer science department. But the math department is very strong one. Not as strong as Princeton, but it is very, very strong. So in general, Rutgers has many good departments. Only the students' body is not as strong as in Princeton. So I chose computer science because I thought that I could somehow work unnoticed and not too much stress on me. I was already, when I got the tenure, 50 years old. Although first time we came here in 86, but only for one semester, it was not final yet. So the family moved in 90. So I joined the computer science department out of the reasoning that I didn't want to go to the very strong department when you have the stress to produce. I just choose the ones which I thought then they were okay. They are not interested in your work, will not disturb, and I simply didn't have the self-confidence to choose the math department.
I wanted to ask you about the way you work. I mean, the way you're most comfortable in thinking about the problem. What do you do?
By nature, I am hyperactive, so I move, or at least I moved up and down. So when I worked and really concentrated, I like to have a long walk. mainly in the forest. Like I really like the Institute of Advanced Studies. There is this forest here. It's absolutely beautiful. So when I really concentrated, I worked. I didn't stay at home. And when I had some idea of if it happens, then I went home and then I somewhat wrote it up. And sometimes, yes, we watched the movie with Anna, and then I realized something, because halfly I watched the movie and halfly, most probably, it's the same with you, and meditated on some things. But mainly walking, that was the real thing. Now, unfortunately, I have some problems, so I have hard time walking. I hope that it will be fixed.
For people who don't know your work, the technical nature, I find it quite difficult in the sense that there are lots of calculations involved. I mean, actually, it's not just, you may have an idea, maybe philosophical in some nature, but in most cases, or in most papers of yours, and I know many, it's not just, you have to do computations where there are many parameters involved, and their relationship is really critical to whether the argument will work or not. So this you do in your head.
When I was younger, I did. And when I went home, I checked it, and then most probably sometimes there was an error in the computation, and then I wrote down. Well, once I was getting older, then I had so I took a paper with me and a pencil, and then I sit down and then.
Cheating.
Yes, exactly. This was illegal, but this is already a cheating, yes, to get older, right? So now I cannot do the things, and I just walk. Still, I walk even I have some physical problem, but I have the paper. I cannot keep now anymore the computation. I don't remember. And then also I am afraid, then as you said, if there are many parameters involved, that I write it up.
I'm amazed that at any age when people can do these kind of things in their heads. You were not a standard product of the Hungarian factory of mathematicians, in that in high school you didn't go to one of the mathematics schools like Fezekes, and at the time these schools were extremely successful at producing very, very bright mathematicians that many became leaders and so on. After the Soviet Union collapsed, there was some change, definitely in Russia and in the ex-Soviet Unions, in the investment of resources into these things. So what is the status of this education of bright mathematicians, maybe physicists nowadays?
I don't know exactly, because I have now only the grandchildren who are attending school, but they are not in the high school, and none of them are mathematically oriented. But what I know is that maybe after the collapse of the system, the schools, the elite schools, did not collapse for a while. Now, I don't know the present situation, whether they pay so much attention. That I really don't know. How it is with the elite schools, and I doubt that in the other high school the education is good. At least teaching mathematics is not so good. Well, for that you need teachers, and then most probably we lack the teachers' body, so it's just too small. There are not too many good teachers. All times the teachers had some respect. Now it seems to me that even in the high school very strange things happen. So what happens in the elite schools, that I don't know. But in general I have some feeling and that the high schools, our high schools are now a little bit, well, it's not the same as when I was young. Now my theory, but it doesn't have to be taken seriously. I am more for the Prussian, Russian methods, and when in the school you have discipline. And then the teacher tells you what to do, of course, not to the extreme, but somewhat. This is my model. And also, I believe that I am not talking about Fazekas and about these elite schools. In my time, I visited this regular, usual high school. So they try to teach even the students who were not that great, like in like C+, so on the middle. Yeah. And they got something out of even the in mathematics and in any other subject. And then who wanted something extra, we had a special classes after the school. If you wanted, then you could take part of it. Now maybe this is unfortunately worse, I am almost sure. So I hope that at some point they will realize, and just speaking only about mathematics, that mathematics is extremely important, not the subject itself, but the way of thinking, and then it can be conveyed to almost everybody. I don't want to say everybody, but definitely somebody who is on the middle. Just that the idea that you state something, maybe you have to prove, so you have to somehow support your claim, and then also the way of proving, then you try to find some connection between things. So if somehow the students could be taught so that part of mathematics, then the nature of mathematics, they could understand a little bit, then it would help a lot in their everyday life. But for that, unfortunately, you need teachers, good
but actually,
teachers.
I expect you to agree with me that to do this successfully, actually, combinatorics is a fantastic subject to teach in elementary and middle school and high school, because the reasoning you need to do there, and it's much more concrete. And the interest of students in many of these problems, which are elementary, you can draw figures, you can talk about games and puzzles, and nevertheless which is what combinatorics is about, and you are still doing mathematics. So maybe actually in Hungary it was a significant part of the high school mathematics.
And we had a problem, which we called, yes, you have a small problem when you had to reason, and then we could consider it as a problem in combinatorics, solve this puzzle or that puzzle. Yes, that was a part. And this is, elementary geometry is, and then combinatorics most probably are the two subjects which may be the most suitable for that purpose. I don't want to say then, of course, you don't have to learn how to compute the volume of the sphere or something like this, but if you cannot learn it, it's not good, but it's not end of the world. But if you just get a little bit feeling then how to connect things, and also really require from yourself a kind of something which is similar to the notion of proof, then you get a lot. And for that, combinatorics, yes, I agree with you totally, somehow has the nature that it definitely would be maybe the most powerful subject in that sense to teach.
I know there is, I guess it's related to drawing children into mathematics. There exists, and I think it still exists today, this journal, the Komal, for the high school, or for students before college, which has mathematics problems. Can you say something about it?
Yes, it's something like in every month you get 10 problems, maybe not 10, mostly mathematics, but also from physics, and you solve it, you send it back, and you get some point, just like grading midterm exam, and then the end of the year they add up the points, and then and you learn a lot if you really consistently do them. Actually, I would even say that if you are in engineering, obviously, yes, it helps a lot. It's no question about it, which is said mathematics needed there. But even in the subject when mathematics is not needed, even just a little bit, not to be the first or second, just follow a little bit or solve some of the problems which you can might help even people who are basically in humanities. So I am very much for it. But something which is very nice, now that I got some kind of recognition in Hungary, so they are asking me to go to the schools, and then I talk, and then even there are these summer camps when not the Fazekas summer camp, because that is summer camp most probably organized by Porsche, the great teacher and the great person who really catches all this genius and develops them into the mathematician, but not just ordinary, or maybe but with some interest in mathematics. Parents and I, with Anna, we have been in 3 different such a camp, and it was very nice to see that they were interested and asking questions, and it helps them. So in that sense, still I am not pessimistic, but maybe then if you consider the education in the high schools, that is not on the same level as it was in my time, but maybe I am just biased, and also I have no complete information about it. You could ask the others who are much more in the teaching, and they could give you a little bit more fuller picture of it.
I think people look with envy to Hungary. I mean, at least I am. I mean, both in Israel and in the United States, I think the general public does not recognize mathematics as a valuable thing. I mean, governments, they may receive a singer or a soccer player, or if the team does well, then there's the papers rave about it. But if mathematicians do well or get prizes, or a team of kids go and win, so it's not a big deal.
We are living in the age of television, but in Hungary this is the same as in here. The celebrities are the ones who are not in mathematics.
It's just a level.
But maybe somewhat more interest. They are somewhat more interested in the so-called ordinary people than here. But it could be then it's just too big country. No, but Hungary traditionally science were recognized.
Other thing that is related to the education and upbringing of these young stars is it's not just teaching in schools. It seems that there is the mentorship, the availability and the motivation of people like Pozha is a great example, but I think of teachers willing to talk to kids after school, of professors, famous people like Erdesh and Turan and Shosh, and meeting young kids and bringing them home and discussing mathematics with them. So this idea that education goes beyond the school, and this, it's very rare, at least.
Yes, I don't know other countries, but yes, it existed in Hungary, and it still exists in that sense that, yes, you visit these schools, and also, yes, if you know somebody just on personal level, you talk and try to...
But you get to know them, and you get from your friends, you get to the...
Actually, there are meetings in every year in the countryside, big meetings for when kids. The students for kids, and the teachers are there, and then they invite so-called, that's just so-called famous, of course in parentheses, mathematicians.
Famous in our world. People
Well, in
yeah,
our
yeah.
community, they invite, and you are there for the whole day or maybe for 2 days.
Yeah. Since you said you started, your father wanted you to be a doctor, a physician. How did you really end up with mathematics?
So after I dropped out of the medical school, I went to work in a factory. So I really did a very hard physical work for almost 2 years. And then what happened? Then I was always short. Really, that's a big problem if you are short. For instance, I never learned how to dance because when I was like 16, then they arranged, at that time there was exclusively only for boys or for girls, the high school. So the gym and the teacher of physical education invited the girls from the other school, and then in the big gym we had to dance, we were supposed. So then a girl chose a boy, and so I remained, the only one who remained, and we were about 100. So I remained, and then one girl remained. I wouldn't say, well, you don't judge people by the look, of course. But nevertheless, so that girl didn't most probably never would make as a movie star, unless of course if she played some character.
Appropriate.
Yeah, so she was ugly practically. And then I had to ask, so that was only 2 of us remaining, and she refused to dance with me because I was short. And then I decided I never will learn dancing, and I never learned dancing. Actually, at the end of the year, the last day, around 11 o'clock, we always dance with Anna Walser, but only for 2 minutes. That's all what I do. So for me, it was very bad. I couldn't care if they said anything, beat me up or anything. It happened actually because I was weak, but shortness is very bad. And really, I was really short, but much shorter than Messi. Now, Messi was 131 when he was taken for Argentina to Barcelona, and he was 13, and I was 14 when I was 121 centimeters, of course. So I was really very short. I remember when I was 17, I was still 149. And then in a year, and then not that I am tall now, I am about on the middle, but so more or less I am now tall enough to get to be able to get at least one girl. I meaning my wife Anna, so she was willing to marry me. So this girl didn't. So and then I very much admired the people who are tall, and the mathematician in the class was a tall guy, the tallest. And then whatever he said, you said that you believe anyway whatever I say. Now I believed more than whatever I said. Even I believe what he didn't say. So I believed everything. And he became a mathematician. And when I worked in the factory, but nevertheless I sometimes went to the center of the town. And this guy was well liked by the girls. He had the right look too. And then he was standing at some place. I was a little bit surprised, and then I ran into him. So what happened actually, then he was 15 minutes late, and though he was a very tall and good-looking guy, the girl left.
Amazing.
Hadn't he been just maybe 10 minutes late, then I would have never been a mathematician. So we started to talk, and then because he was my good friend from the high school, he told me, then why don't you try to go to the same university, because he knew that I was a good mathematician in the high school. So I easily could solve the problems, and I always got A. and I helped the others so I had no problem with mathematics. That was clear that was easy for me and I liked it. Just because of my father, I studied biology. And then he told me, and then because he was still tall, of course, he was at that time about 20 or 21 years old, so I took his advice, and that is how I went to the university.
But you think that if you never met him, you just continue working in the factory, you were reasonably happy there? No.
No, you don't want to, it's a hard physical work. Most probably I would have chosen maybe this one because it was easy to get in, because it was not a well regarded profession being a math phys teacher. 200 people they actually took, so admitted, and even they couldn't fill the whole class, so after the summer, after the end of the summer, or at the end of the summer, they actually still had to have an extra entry exams, and then they could fill. So it was not the most respected profession, so maybe I could have, maybe, but it is not clear. But of course, we don't know it, and anyway it sounds much better this way then you just go there, then because of the influence of a tall guy, you choose your profession.
So we all need to thank him. This is Elman, no?
Yes, he's Elman, yes, and I plan to meet him. Now we met almost regularly, once in a year or so. He lives in Dutch, but he comes quite often to Hungary and vice versa.